In this presentation, we're going to go over the four rules that we already have: arrow out, ampersand in, ampersand out, and wedge in. And then I'm going to also introduce arrow in as our new rule. It's just good practice to keep going over these old rules just so you keep on being familiar with them. So if you remember, our arrow out rule is that if I have a conditional statement and I have its antecedent, then I can write its consequent from those two statements and sliding arrow out. So I always use squares and circles for these just because whatever we want to put in there works just as fine. So say if I had P and Q, arrow T as an assumption, and I had P and Q as an assumption, then I could write T from 1 and 2, arrow out, because here is my here's my antecedent in 2, here's my consequent, and then moving it down there. So that's the arrow out rule. Then with our ampersand in rule, our ampersand in rule is quite simple. It's from just saying that I have two different things, and then from those two different things, I can just put them together. So I cite the two different lines in which I'm getting my conjuncts from, and that's that. So say if I had P and Q as assumptions, then I could write P and Q, 1 and 2, ampersand in, 1 and 2, just like that. I could also write this equally as well. So that is our ampersand in rule. Now, once we get to ampersand out, it's just the reverse of our ampersand in rule. So it says if we have a statement that's got an ampersand in it, then we can write either one of the conjuncts using our ampersand out. So say if I wanted, or say if I had the statement P and Q as an assumption, then I could write P by itself from 1 and out, or I could write Q by itself also with 1 and out. So that is ampersand out. Next we have our wedge in rule, and our wedge in rule is probably the easiest one. The wedge in rule just says that from anything, I can wedge in anything that I want. So say if I had P as an assumption, I could write in line 2 anything that I want. I could write P wedge Q from 1 wedge in, or I could even write something as elaborate as Q arrow T. So I could wedge in anything that I want next to a disjunct that I already have given to me in one of the previous lines. It also doesn't matter which way in which I write these. I could write Q wedge P, or I could have written Q arrow T wedge P. It doesn't matter what I wedge in next to something, as long as it's given to me previously somewhere in the proof, I can wedge it in that next line. And when we want to wedge something in, that wedging it in is going to be telling us that there is something specific that we're looking for in our proof to build, and that's what the wedge in is more than likely going to be used for. This gets us to our new rule. So our new rule is going to introduce something new to the proof structures. So before, we've had our numbers that are just our line numbers, that we list going so far down. Then say if I have assumptions that are given to me in the proof, like this. So say if I were given this sequence here, I could prove it. What I do is I take my assumptions, I write them in the first lines, and then I'm looking to prove my conclusion at the very last line. And in these line numbers, we have derivations. And in this line, we have justifications. And that's where we're going to use our rules. Now that we get to arrow in, and we'll also need it for when we do tilde in, tilde out, we're going to have a new type of justification, a new thing that will go in our justification line. And that is going to be what's called a PA, or a provisional assumption. This is an assumption that we make prior to starting the proof, or we can make it further down the proof too. It just depends on what we're trying to prove. But the idea of provisional assumption is we say, if this were true, then could we prove what we're looking to prove? And so as we go through this arrow in rule, you'll see that a PA is the first step in every arrow in rule, or every arrow in proof that we have to do. Because we're saying, well, if this was the case, would we get to this result? So let's just look at the rule itself. I'm going to get rid of this up here. Erase all of this stuff. And here is the basic proof, or the basic rendering of the rule itself. It says, from some statement that we make as a PA, we build towards a conclusion that we're looking for. So this is the conclusion that we're looking for. And possibly better to call it consequent. So it's the consequent we're looking for in the arrow in statement. Then from our PA and arriving to the consequent, we can derive, or we can use arrow in to, there we go, sorry, got these assumptions backwards. We can build the arrow from 1 and 2, arrow in, and then it'll be 1 plus all the other numbers of the assumptions that we'll have later on, and really that's what 2 is going to be as well. It's going to have to involve the PA somewhere, so the PA has to be part of deriving the conclusion. And so as you derive the conclusion, or the consequent you're looking for in the conditional statement, the circle part of the conditional statement, once you get to the circle part, you should have the PA, the number associated with the PA, somewhere over here, which is 1. Then the important thing is that when you do arrow in, same thing will happen when you do tilde in, tilde out. You remove the PA from your premises that you cite over here on the left-hand side. The reason why is that you kick out the PA as you derive a conditional statement. So once you make the conditional statement, it's saying, well, this PA goes away because it leads to this specific statement, this specific conditional statement that I'm going for. So let's just do a couple sets of problems, and you should be able to get a better feel for what's going on with this new rule. So probably the easiest proof that we can do is something like this. It's typically considered the chain rule. If we were doing derived rules in this class, you would be able to do this easier, but we're not doing derived rules, mainly because you don't need them in here. But this is how we do conditional proofs. So first thing, same as every other proof, we start by listing our assumptions and we mark them with A's for assumptions, like so. Then we're going to look at our conclusion like we always do too. And what's the main operator in the conclusion? Well, the main operator is an arrow. And that's going to be your hint as to what you're going to need to do in the proof. Because if your conclusion is an arrow, you're going to assume the antecedent and you're going to look to prove the consequent. So we'll assume P, and this is a provisional assumption, so we need to mark it as a PA. And since it is its own assumption, it gets associated with the number in which it appears. So P appears on line 3, so we associate with number 3. Now, with this, what can we do with our proof? Well, we could toss this P into the conditional statement 1 to get T. So 1 and 3 give us arrow out, and 1 and 3. Then we can take this T and we can toss it into the conditional statement 2. So that will give us 2 and 4, arrow out. And so 2 has 2 in it, 4 has 1 and 3. Now we got to the consequent that we were looking to build in our conditional statement. That consequent depends upon our PA, number 3. So in line 6, we're just going to write P arrow Q. And that's going to be from 3 and 5. And we're introducing an arrow between them. And we're going to have 1, 2, 3. But, as I mentioned in the previous slide, whenever we have a PA and we build an arrow in, or a tilde in, or a tilde out, I know we don't have tilde in, tilde out yet, but once we get there, it'll be the same rule. We remove the PA that's associated with the building of that arrow. So really that 3 goes away. It drops out. The reason why is the assumption drops out as we build the arrow. Because it's saying if you had this, then you would be able to get to this result. And what I like to do in these situations is show you the same proof, but have a different conclusion. So this proof on the left is the same one as this. Because a conditional statement as a conclusion is just saying, if you had this thing on the left-hand side as a premise, could you prove the right-hand side? And so if we were to do this proof here, now this time the P would be just a regular assumption because it's not something that we have to add, but we would have this, and then we would toss the P to get T out, so 1 and 3, arrow out, 1 and 3, and we toss the T in there to get Q, and then that would be 2 and 4, arrow out, and then 1, 2, and 3. So it's the same exact proof on both sides, just there's one set missing, mainly our conclusion to build the arrow. But that is the conditional rule. That's what we're doing when we're trying to introduce an arrow, and especially if our conclusion's an arrow, it's saying if you had this thing as an assumption, would you be able to prove the right-hand side of it? And so in most instances, what we're doing is the same exact thing as we would do over here. We would have the left-hand side as an assumption, and then we would look to get to Q in both places. How we end up changing that into a conditional statement is by having to assume the left-hand side and then working to get to the right-hand side. And then we build the arrow and we kick out the 3. So this 3 is imaginarily there. So that is the arrow in rule. We'll do a bunch of problems that focus on the arrow in rule. So just know that there is sort of repetition to it, just like with all the other proofs. You start with listing your assumptions. Then you look at your conclusion. If your conclusion is a conditional statement, assume the left-hand side, look to create the right-hand side. So assume the left-hand side, the antecedent, look to derive your consequent or the right-hand side of the conditional statement. And then once you've built the right-hand side of the statement, you just arrow in, citing the left-hand side that you create a PA for, and then the consequent, which is the right-hand side. And then you cite those 2 lines, and then you'll drop out the premise that is associated with the PA in the premise justification on the furthest left-hand column of the proof itself.